So here's a topic that we've kind of touched on previously, and we've kind of avoided using the more mathematical versions of some of these. And so what this lecture is devoted to is looking a little more using numbers, looking at this idea of probability. So probability is something you might have run into in other classes. It certainly comes up in statistics, and we'll see a few cases where it comes up in genetics. It's been underlying a lot of what we've been doing so far. We just haven't really spelled it out as such. So I think you might see this term and get a little scared that we're getting into some heavy math. We're going to do kind of probability light for this one. And maybe as we get started, you can think about it as something a little more friendly. When you say probability, it's related to this word, of course, probably. So when your friends ask you, are you going to the movie with us tonight? And you say, probably. That means that there's a chance that you will and a chance that you won't. And maybe in your mind, you have an idea of whether that's more or less likely. You might have a 90% chance of going, very good chance that you would go, as long as nothing crazy lines up in your way. Or you might have a very low chance of going, or you think you're barely going, but if you're otherwise really bored, you might go with your friends. So probability can range from very likely to very unlikely, and it's an important concept for us in genetics, which is why we're covering it here. So my intro image here, this is a lightning strike, and probability is something you might have heard about relating to something like a lightning strike. What are your chances of being struck by lightning? They're more than zero, and they're less than 100%. You're not sure you're going to get struck by lightning, and there's more than a completely zero chance that you would get struck by lightning in your lifetime. So here's one a little bit closer maybe to genetics. If you have one of these phenotypes or diseases or conditions that you might get in your lifetime that might have a genetic effect. So you might be concerned about your individual chance or someone in your family. What is the chance of developing lung cancer? So here we have the chance that a person will develop lung cancer in their lifetime is about 1 in 15. So think for a second about what that means, right? For you individually, basically knowing nothing else about you, they don't even have males and females separated out here, knowing nothing about you, where you live, how old you are, how wealthy you are, just a person, the chance that a person, may be weighted by people who live in America from the American Cancer Society, but the chance that a person will develop lung cancer in their lifetime, 1 in 15. So think about what that means. Think about how that might affect your life, your choices in life that might influence your chance of getting lung cancer. Is 1 in 15 a lot? Is that low? Is this a risk worth addressing, or is this a risk worth ignoring? All right, so let's get into something a little more concrete here. So when we look at probability, we're often looking at fractions or ratios. So real basically here, when we look at probability, we're looking at a range between 0 to 1. So we have 0 at impossible to 1 of certain. And any one outcome, when we use the field of probability, we're looking at something that's probably lying in this range between 0 and 1. So we'll see some examples of gambling. Gambling has some nice probability tie-ins that are also good for life lessons, I think. So if you have, let's say your friend's doing a card trick, and you pull a card out of the deck, and they say they're going to guess the card that you have. So without knowing anything else, what are the chances that they would know, or the chance that, say, if you just predicted ahead of time that you were going to pull a 6 of hearts, what are the chances of getting a 6 of hearts out of the deck? So the odds of that, as it shows here, this ratio fraction, one card. So one of the cards in a standard deck of cards is a 6 of hearts, and the total number of cards in the deck is 52. So 1 card out of 52 is the 6 of hearts. That means you have a 1 in 52 chance of drawing a card that is the 6 of hearts. This is one of the reasons we're surprised when somebody successfully guesses our card. It'd be pretty hard to just randomize and have a person guess exactly the same card that you're going to pull out. And that's usually a card trick, right? Somebody knows what's going on behind the scenes. So we have a specific outcome here, what we're kind of interested in observing, and then all the possible things we could have observed. And that's going to turn into a fraction. And we'll see that that fraction, anything where the numerator is lower, smaller than the denominator, that's going to turn into a fraction that's less than 1. And we're dealing with positive numbers. So again, reminding us that we're working between 0 and 1. Let's say you were drawing from the deck of cards and you wanted to say, what are the chances that I'm going to pull a red card or a black card? And that's all the cards in the deck, right? So card without jokers. You could do the chance of pulling a card. If you pull a card, what are the chances your card is going to be a card? It's 1. So there's sort of a range there. Certainty, 100% certain that if you draw a card from the deck, it will be one of the cards that's in the deck. Another way to phrase maybe the opposite end of this is what are the chances of pulling a card from the deck and having it be green? So green is not a color in the standard deck of cards. You would have a 0 out of 52 or 0. So you can, if you're maybe looking at things unreasonably, you could find outcomes that are downright impossible and outcomes that are downright certain. But typically we work with things that are in this middle range here. And lots of genetic applications. If a person wants to get into a career like genetic counseling, people would like to know for themselves, for their children, what are the chances that my child is going to inherit something that my family has? What are the chances just in general that my child has some feature that might have a genetic tie-in? All right, so maybe a little more extreme examples here. You can calculate out the chance that a person will get killed by a cow in their lifetime. So it turns out that cows kill 20 people per year. So thinking about your individual chances, this might seem a little high, right? The average person has a chance of getting killed by a cow. You could probably think your way through this and say, well, if I'm not running into cows on a daily basis, I'm probably on the safer side of cow murder. But if a person works with cows and they're day in and day out involved working with cows, they might have a much higher risk than the average American for getting killed by a cow. But you could also calculate this out too. Same thing as we did before, number of outcomes you're interested in. So deaths in a year per 328 million people. That's a pretty low chance for any one person. So 1 in 16.4 million, pretty low chance that any one person is going to get killed by a cow, thankfully. I don't like the way the cow's looking at us though. All right, so getting back to genetics, we've worked with this before, and I just want to kind of reinforce the genetic principles in light of probability. So we saw the chance of producing a certain kind of gamete. So that was one of our Mendelian laws here. Let's say we have a person who is heterozygous. And they go through the process of meiosis. And each gamete is going to get one of those chromosomes. And I'll just simplify it down. A lot of times when we're looking at gametes, we are just considering one at a time. When people fertilize eggs and have babies, it's one at a time. What are the chances that mom's little a allele got into that egg? So one of these gametes, this egg cell, what are the chances that it has little a? Well, we have an outcome of interest. and it could have been big A or little a, right? So we have the little a is the thing we're concerned about. What are the chances it was little a? Could have been big A or little a, so that's one outcome over two possible outcomes. And an important part that we've reinforced a lot of times is that big A and little a have to be equally likely in this case. And that is something we observed through the principles of the Mendelian principles, and also something we observed in meiosis, where these chromosomes are randomly going into two sides of the cell, and each side of the cell has a chance of becoming a gamete. So it's a nice, clean, two possible outcomes. One of those is the one we're interested in. That's a 1 out of 2, or 50%. Let me just phrase these all in here. So 50% is a percent version of 0.5 is what you would get by dividing 1 by 2. Any of these is an acceptable way to frame probability. So again, a number between 0 and 1, it's half likely to get little a versus big A there. All right, so gametes, odds of gametes combining in fertilization. This is something we saw before. When you look at a Punnett square, so if you have mom being big A, little a by dad being, let's change it up a little bit here, dad can be homozygous. And if we do a Punnett square here, mom gives in big A or little a. Dad, on the other hand, in this chance here, his probability of donating a little a to his sperm cell is 100%. So little a is one of the possible outcomes, and there's only one type of outcome. So there are two alleles here, but they're both the same, and the denominator there is not little a or little a, because it's only little a. So dad's chance of having little a in his gamete is 100%. Mom's chance of having little a in her gamete was 50%, as we saw before. So the combination of these two, the Punnett square is a way that we're illustrating this probability. So the chance of 100% event combining by some 50% events gives us two possible outcomes, and each of these are 50% likely. And that's because the Punnett square shows us outcomes that are equally likely. We have two of these outcomes. One out of the two possibles is big A, little a, and one out of the two possibles is little a, little a. And I guess I'll mention here another factor of probability is that all possible outcomes should add up to 1. Let's put 1.0 so that stands out as a number a little bit more. So if we add 50% and 50%, we get 100%. If we add 1/2 and 1/2, we get 1. If we add 0.5 and 0.5, we get 1. And so that means that we're covering everything that could possibly happen. Of course, there are sometimes little exceptions in biology, but we got to simplify a little bit here. Okay, so we've been doing probability all along with Punnett squares and Mendelian laws, but now we're getting a chance to think about them a little more mathematically in this topic. So here we go, segregation of alleles, just like we did before. For any allele that's heterozygous, for every gene that's heterozygous, each allele for that gene has a 50% chance, equal chance of big B here or little b, equal chance of little q or big Q. And in the chromosome 3 here, we've got only big N, so that's 100% chance. I mean, realistically, you're looking at a 50% chance of this big N or this big N, but genetically, we wouldn't be able to tell the difference on that. Independent assortment, just like we did, I guess we haven't done this one yet. We did, a while back, we did gamete squares. And so you could look at the question of getting a big B with a little q. Let's look into that a little bit more detail. Okay, so let's say we have a parent, big B, big Q, little q. We'll just do 2 genes for now. Odds of a big B, little q gamete. So you could do this as a gamete square. Which is what I like to call these so we don't get them confused with Punnett squares. It looks like a Punnett square, but we're combining the alleles for one gene by the alleles for another gene. So B's and Q's, big B, sorry, shouldn't talk through this. So 4 possible outcomes, big B, big Q, big B, little q, big B with little b with big Q, little b with little q. And one of those possibles is here. So that's 1 outcome out of 4 possibles. There are other ways to figure this out. If you're comfortable, you can just do other ways that we've seen to combine alleles from different genes. And so that's 1 out of 4 possible gamete combinations. They're all equally likely. Again, if you remember, this is unlinked genes. And we've seen some whole different considerations when it comes to linked genes that are located on the same chromosome. Probability also factors into that, but not in such a simple way. All right. So back to gambling. So if you are into gambling, I think it's worthwhile to think about your odds of winning. So one of the things they say about gambling is the house always wins. And that's pretty broadly true. So gambling is something that the law regulates pretty carefully. Places that are allowed to have for-profit gambling, they have to be regulated by the state or often owned by the state. And that's because you basically, if you're running your gambling operation cleanly, you shouldn't really lose any money on it for reasons like this. So this is an example from a roulette wheel. I've been told by students that sometimes this isn't exactly how they play out, but this is our roulette wheel for now. On a roulette wheel, you've got reds and blacks, and there's also this outcome which is neither red nor black, and that becomes really important. So this wheel in our example is 18 numbers that are black, 18 numbers that are red, and 1 number that is green. So what are the chances that your spin is going to land on something that's red? You think pretty good odds, right? I'm going to roll, and I'm going to count on landing on one of the 2 major possibilities. So if you've got 18 possibles, these are possible outcomes of interest, and the total number of outcomes is 18 plus 18 plus 1. So 18 over 37, let's see if I can make this work for us here. Oh, I gotta undo my annotation. All right, so 18 over 37, nope, still not working, where are we at? 18 over 37, so turn that into a decimal. If you wanted to turn that into a percent, multiply it by 100. So percent here, decimal there. So 18 out of 37 outcomes that are red. We actually had the same number of outcomes that are black. And that number of green outcomes, oops, let's go over here for green. That was 1 out of 37. So 37 total numbers, only 1 of them was green. And so there's this 2.7% chance of, if you bet on red or black, you could actually bet equally on red and black. And there's a little chance, 2.7% chance, that you would get neither of those as your answer. And then just to reinforce that we've covered all of our bases, I'm going to do the sum of these values adds up to 100%, or the sum of these values adds up to 1. So covering all of our possible outcomes there. Okay, so what that means for probability is if you are betting on red as your outcome, and you think you've got about an equal chance of red or black, that in the long term, you're going to win about half the time and lose about half the time. But your chance of losing, maybe I'll add this in a different row. Your chance of losing would be the chance of things being not red. And so what are the options that are not red? Let's put this in here, you win. So if you bet on red, you win. If you bet and get not red, lose. So how many outcomes are not red? Well, that was 18 plus 1, right? So that's a 19 out of 37, and that's a little over 50%. So in the long term, you're going to win a little less than half the time, and you're going to lose a little more than half the time. And in the long term, if you keep betting, you're going to lose a little more often than you win. And that's where the house wins, is if you keep gambling, eventually you'll lose all your money. That's kind of the rule. So this is my public service announcement against gambling. It's fun, but certainly don't try to bet anything important on it. All right, let's clear that out. Okay, so as we did before, all these different outcomes in fractions would add up to 37 out of 37 or 1. If we add them as decimals, they add up to 1 as well. So we've covered all possible outcomes. It's a good way to check yourself if you're doing a probability test and you want to just make sure you've calculated all possible outcomes. That's a good way to do it, is add up their probabilities. All right. So we did red or black. What are the odds of landing? So let's say you put half of your money on red and half of your money on black, and you figure, well, one of those is going to win, right? What are the odds of landing on red or black? So roulette, one spin, red or black. And the trick here is that you are allowing 2 outcomes of interest. So you can actually add those together. So there were 18 numbers that are red, 18 numbers that are black, and either of those would be acceptable in the numerator here, this outcomes of interest over 37. And let's see, we could calculate that up. So that would be red or black equals, let's see, I'm going to do equals of those two, 97.2%. Red or black. So 0.973 equals 36 over 37 equals 0.973. So not 100% chance, you're not guaranteed to land on either red or black because of that green. All right, what's our other question here? Let's say you spin twice and you want to land on red and then red. So without it knowing anything up front, say you just planned ahead of time and you were going to bet on red and then red again. So this is going to be 2 spins, 2 independent spins. This becomes something different. So we have an outcome which was 18 over 37. And the chance of getting red and red is one of 4 possible outcomes. Actually, I guess we got more possible outcomes. So you can have red and red, red and black, black and red, black and black, red and green. Oh, this is getting big. At any rate, I guess I want to kind of spell out all the possibilities here. Red and green, green and red, black and green, green and black, green and green. I think maybe that's all of them. So it's one of a lot of different outcomes, and each of these outcomes now is not equally likely. I guess I'll maybe just give you the answer here. If you've got a situation where you need two things to come to happen together, you need red and you also need red on the second spin, that becomes a multiplication, where you multiply the chance of the first thing happening times the chance of the second thing happening. So that becomes when we've got to probably do our math on over here. All right, I'm just going to do this one, red times, same thing again. So 237 equals 0.237. So this outcome here was pretty likely in the scheme of things. Pretty likely, you can kind of picture on the roulette wheel, pretty good chance that the ball would fall into red or black, right? 36 out of 37 chance. But the chance that it was red and red would have to have two sort of unlikely things happen together. And those are also, they're about as likely, say we just kind of ignore green, there are four of these major outcomes. And so one of those outcomes is about a quarter of the total outcomes, pretty unlikely. So if you are a person who wants to keep betting, you think red is your number for the night, your odds of continuing to get red as you increase the number of spins, that keeps going down by about half. All right. So let's maybe simplify it down to something a little more familiar. You can use a six-sided die to do these kinds of, to do the sort of test and prove to yourself what the odds are. So a six-sided die, if it's evenly weighted and fair, it should have a 1 in 6 chance of landing on every possible number, right? So if you roll the die and you want to get a 3, let's do maybe a 4 over here. So getting a number 4 is one of the outcomes out of 6 possible outcomes. Over here, getting a 3 is 1 out of 6 chance. Getting a 4 is a 1 out of 6 chance. On the left-hand side, it's asking the question, what are the odds if you roll one die that your number that comes up is either a 3 or a 4? And again, that continues with what we've seen before. Two possible outcomes, either 3 or 4, and those two are 2 out of the 6 possible ways that things can shake out. So the ones you're not considering are 1, 2, 5, and 6. So you add up, 2 out of 6 is basically 1/6 plus 1/6. In this class, I always have to remind people about adding fractions. So if you're adding fractions, and you have two fractions with the same denominator, then you keep the denominator and you add the numerator values. So to do this by hand, you want to make sure that your denominators are the same value. If you were doing multiplication, just like we saw with rolling the roulette wheel and getting red and then red, if you want to get 4 and then 4, then you got a 1/6 chance times 1/6. And that, to multiply fractions, you multiply the numerator and you multiply the denominator. And this becomes a lot less likely, this 1 out of 36 possibility. Another way to look at these problems is the way that they're phrased. If you phrase them correctly, if you're using the word or is an addition event, so 1/6 plus 1/6. If you use the word and, you're using a multiplication, so 1/6 times 1/6. All throughout this, I just encourage you to be aware of what you're calculating. Just don't go blindly in and start doing addition or multiplication. Make sure you kind of understand the landscape of the question. They're not always going to be quite so straightforward. But we'll try to see all the possible ways to answer this. Here's a way to look at this. So just kind of taking yourself back from the numbers for a second, which of these is more likely to get either a 3 or a 4 when you roll one die, or to roll the same die twice and get 4 both times? Maybe in your experience of rolling dice, right? So say you just need a number bigger than 4 or something, that's fairly likely to happen. But if you need specific numbers and roll twice to get 2 of those specific numbers, that becomes a lot less likely. You could also look at this from the total possible outcomes. So if you're looking over at the rolling one die, as we saw before, we can see the probability of getting not 3 or 4. That was the chance of getting a 1 or a 2 or a 4 or I'm sorry, 5 or a 6. So 4 possible outcomes out of 6. Over here, there's a lot more other outcomes that could have happened. So you could roll, even if you roll a 4, you roll a 4 and then a 1, a 4 and then a 2, a 4 and then a 3, a 4 and then a 4, a 4 and then a 5, a 4 and then a 6. So only 1/6 of the possibilities after you've rolled a 4 are the one you're interested in, and that first one could be in any combination: 1 and 1, 1 and 2, 3 and 5, etc., etc. Lots of outcomes. So that's 36 possibles that we saw in the denominator here, all the ways that the first die and the second die could line up. All right. All right, so let's get it a little bit more complicated here. On the previous slide, we noted that to get 4 and 4, this one's an easier one because there's only one way to get 2 4s. So even if you're not keeping track of your 2 dice, there's only one way to get 4 and 4. The first one has to be 4 and the second one has to be 4. What about getting a 3 and a 4? So turns out there are 2 ways to get this depending on the order of the dice. So it might not matter to look at them, but from a probability standpoint, the first die is a different outcome than the second die. So to show this out, we got a 3 and a 4 is different from a 4 and a 3. So imagine maybe you have 2 different colored dice, or you're just keeping track of them, rolling them separately. The first one is 3 and the second one is 4 is a different outcome than the first one is 4 and the second one is 3. So we can turn this into a statement that's got these and or words in there, and we can use that to turn out our probability. So 3 and 4 or 4 and 3 turns into a mathematical expression. Rolling a 3 is 1 out of 6. Rolling a 4 is 1 out of 6. 3 and 4 together is 1/6 times 1/6. And that's one specific outcome. First one is 3, second one is 4. Or, there's our addition sign for the or it could be that the first one is 4 and the second one is 3, and that's also 1/6 times 1/6. All right, so back to genetics here. Let's say we've got a cross of F2 offspring of pea plants being crossed. We've already worked this out. 3/4 chance of being tall, 1/4 chance of being dwarf. If you've got 4 offspring, what are the chances that all of them have the dwarf phenotype? So you can turn that into a statement that says you need the dwarf outcome, dwarf and dwarf and dwarf and dwarf right? 4 outcomes, all the same. If you use the and, that turns these all into multiplication signs. And dwarf, the individual chance of one outcome is 1/4. And another way to look at that is if you just take the outcome chance of being dwarf and raise it to the 4th power. So same thing as the other expression there. All right, what about being 1 being tall and 3 being dwarf? So this is kind of the limit of how complicated I want to get with this one. 1 being tall and 3 dwarf. So tall and dwarf and dwarf and dwarf is one possible outcome. This would be 3/4, one of those outcomes, and 1/4 chance of being dwarf, 3 of those outcomes. Have we covered everything? So this is one way to have the outcome, and it's influenced by the order. So in this way that I've written it, the first plant, the first seed you plant from that cross turns into a tall plant, and the other 3 turn into dwarf plants. That's one of the possible outcomes. The other possible outcomes are that the first one's a dwarf, the second one's tall, and the other 2 are dwarf, or dwarf, then tall, then dwarf, then dwarf, then dwarf, then dwarf, then tall. And I think you can do this by hand. If you've got one that's different from the others, that one could be first, could be second, could be third, could be fourth. So I'm going to do a little bit simpler than I usually do for this one. And what this tells us is there are 4 ways for this to happen. In every outcome, it's one of the outcomes that's 3/4 chance, and 3 of the outcomes that's 1/4 chance. And so all this together, if we have 4 ways for that to happen, that becomes a 4 times that value. So this is the full equation for calculating that: 1 tall and 3 dwarf. This kind of thing is good to get some practice at using your own numbers. I'll give you some practice problems on this kind of thing. All right, so we saw 4 ways to get that outcome. Here they are spelled out. So again, just it's a little bit complicated, but the easiest version of the complicated stuff is one different from all the rest, and that one can be the first, the second, the third, or the fourth. All right, so that's all I'm going to ask. That's like the most complicated I'm going to ask you about these. Some number of outcomes and potentially one different from the rest. All right, so let's keep going with probability and kind of our standard genetic crosses. And here we've got a cross between double heterozygous mom. So mom's big Q, big N, little n. Dad is big Q, little n, little n. And let me just write these out for our reference. So mom, big Q, big N, little n. Dad, big Q, little n. What are the odds that they have a child with genotype little q, little n, little n? So little q, little n, little n. So up to this point, we've been doing Punnett squares, and I'm going to show you a shortcut that can save some time on getting to the same answer. So why don't we go ahead and do the Punnett square? You can do the gamete square if you need to. I've got a pretty good handle on these. So big Q can go with big N or little n. Little q can go with big N or little n. Dad's got 2 kinds of gametes. He's got only 1 kind of N, so that's big Q with little n or little q with little n. I could fill this whole thing in, but I think I can just maybe show you that the only way to get 2 little q's and 2 little n's is that the gamete from dad has to have only little q and little n, and the gamete from mom has to have only little q and little n. So that's 1 out of, again, Punnett square, 8. Now 4 by 2, 8 equally likely outcomes. So that's a 1/8 chance of that outcome. All right, another way to look at that is if you look at, look at your genes independently, and you're going to cross the chance of having little q homozygous, of getting little q homozygous in the offspring, and also little n. So what you could do with that is your Punnett square for the individual parents. So this was a 1/4 chance for the Q's, and the n Punnett square was 1 kind from dad, 2 kinds from mom. And so in the n Punnett square, there are only 2 possible outcomes, and 1/2 of those was the little n. So if you calculate this and that separately and say they both have to happen together, that's a multiplication. 1/4 times 1/2 equals, multiply the denominators, 1 out of 8. So same value, got it through 2 different ways. I'd like to give you lots of chances to explore this in different ways. So Punnett squares also mathematically, get you some practice doing those. All right, let's see what else we got here for questions. What about a child with the big Q phenotype and the big N phenotype? So that would be, try not to take up all my space, big Q blank, big N blank. So let's see, over here we've got, well, I won't fill them in, I guess, but I'll put an X where everywhere that would be satisfied. So getting a big Q and a big N here. This one would have the little n from both parents, so that wouldn't work. This is a big Q combined with big N. This one has only little q's, and then this one has only little n. So we got 1, 2, 3, 3/8 on there from the Punnett square. Over here, we've got of the q's in the Q Punnett square, everything except for that 1/4 was something with a big Q. So that was a 3/4. Sorry, I've got too many fractions here. And then over here, big N was 1/2. So 3/4 times 1/2, getting a big Q 3/4 chance, getting a big N 1/2 chance. Both of those together, multiply the numerators. 3 times 1 is 3, multiply the denominators. 4 times 2 is 8. Same value through these 2 different methods. So that was the phenotype that goes along with the dominant allele for each. And little q and little n, I think we basically just did that. So there's this one, the only way to get the little q phenotype and the little n phenotype, that's the one we did before. So we'll kind of skip that for now. We already did it. All right, one last thing here. This is an interesting case of a family in Michigan that had 14 children, and all those children were boys. No regrets. What are the chances? So this obviously makes news. This is something you would look at and say, wow, that's surprising. And it's surprising based on, I think we have a pretty good innate expectation of probability. So what would we expect? In 14 kids, what do we think is more likely? So more likely, 14 kids, you might assume equal, right? So we've kind of worked with equal chances of boys and girls. Seven boys and 7 girls. And what are the chances that all are boys? So this would be a 1/2 chance of each child being a boy raised to the 14th power. And I think I want to change the way I've written this because I didn't give you all the tools for it. Hold on. Chance that 13 are boys. So it turns out actually that this family had a follow-up story where they have their 15th child. They kept going, and their 15th child actually was a girl. But let's stick with 14 here. Let's fill it in. All right. Nope, I'm going to stick with that. So how much more likely is it to have 14 boys or to have 13 boys and 1 girl? So 14 boys was 1/2 chance of having a boy raised to the 14th power. The chance of having 13 boys and 1 girl gets a little bit complicated here, especially because we've got 13 of them. So let's see if we can maybe spell out what all would happen there. Okay, so let's say we had the girl first. Girl, boy, 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 boy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You think it's hard to write this many B's? Think about how hard it is to have 13 boys. All right, so maybe we could just think our way through this. We've got 14 slots here. And there'd be 14 places to put a girl, right? Girl could be first, could be second, could be third, could be fourth, fifth, sixth, seventh, 14th. So there are 14 ways to have 1 girl. So each of those, each outcome would be 1/2 chance of having a boy 13 times, raised to the 13 power. And it's actually the same outcome we're using for a girl, just one of those. So this outcome, 1/2 raised to the 13th power times 1/2 is actually the same thing as 1/2 raised to the 14th power. The thing that's different, sorry, I went over here, is that there'd be 14 ways to make that happen. So it's every individual outcome is an or. So girl first or girl second or girl third or girl fourth, 14 times. So whatever the outcome is, it's 14 times more likely in a family of 14 kids that one of them is a girl than that none of them are girls. And maybe even more than requiring the specific outcome of 14 boys, it's just the chance that you get a few different ways to have the same outcome with this 1 girl means it's a lot more likely. We could calculate the 7 boys and 7 girls outcome, but I haven't given you the tools for that, and I think I'm gonna, since we're doing this virtually, I'm gonna skip that part this time. All right, no regrets, maybe a little regrets.